In the last video, we combined the return to Lib-C attack and the format string vulnerability attack from the two videos before that in order to leak the pi address with the format string vulnerability, and then we leaked the Lib-C address by overflowing the buffer and using puts to put out the global offset table address. In this video, we're also going to use a format string vulnerability, but there's going to be no buffer overflow this time around. We're going to use the format string write operation, which we touched on very briefly in this video, and we're going to use that to overwrite an element of the global offset table. As usual, we'll start off by doing some basic file checks. Let's go and see what we've got here. You can see that we've got the binary set to being owned by root, again the same with the flag. I'll not go through the commands again, I've added them to the GitHub, so in most of the challenges you'll want to do this to make sure the flag is owned by root, and the same with the binary and that it has the sticky bit set. Let's go back here. So first of all, we'll check out the file type and the global offset table overwrite binary. It's a 32-bit executable this time. You could do this in 64-bit as well, though it's just going to be bigger addresses. It's dynamically linked, so it's going to be using the Lib-C library, and it's not stripped, so we can see all the function names and things like that. Let's also use checksec and see what protections we've got enabled. So once again, we've got our NX enabled, so we can't expect to execute code on the stack. If we are able to overflow the buffer and inject code, it won't be executed. We've got stack canaries this time, which I'll touch on very briefly whenever we have a look at this in Ghidra, but the next episode is going to be focused specifically on canaries and how to bypass this protection, so I'll not go into too much detail. We have pi disabled this time. We had it enabled last time because we were leaking the pi address, and we could actually do that again this time because we're dealing with a format string vulnerability. But I've just set pi to be disabled just so we can focus specifically on the global offset table overwrite. And another protection we haven't mentioned is this rel row. So this is specifically to do with the vulnerability that we're going to be looking at. If this was set to full rel row, we wouldn't be able to overwrite the global offset table address. This basically defines the readability and writability of the global offset table. So let's check out the source code. And a very basic program. We don't have any buffer overflows this time. We can see it's using fgets, and it's making sure that the size of the input that we read into the buffer is the size of the buffer. So it's going to take our standard input, it's going to make sure that we're only reading 300 bytes of it into this buffer, and then it's going to printf. So this was the dangerous part. Remember that if they don't specify a format specifier here to say that they want to print printf as a string this time, the buffer as a string, then it allows the attacker to do that instead. And the attacker can specify, let's say they specify string, it will try to, well, in the case of a string, it'll actually treat it as a pointer, the value that we entered in the standard input. But that's only for the first element. So for example, if we did %s, that would take the first element. But if we do %s, and keep doing that, it's not just going to print out the value that we've put into the stack, it's also going to start printing out all the other things that were on there, including the local variables and Lib-C addresses and things like that. That's about it, not too much to look at here. Let's go and take a look at this in Ghidra. So I've already got this open, and we can go into our functions, have a look at the main function. Again, we might want to go and start renaming stuff. Notice that it's a little bit different this time because we have the stack canary. So there's actually no buffer overflow, so there's no way that we're going to trip off the stack canary anyway. But if we hadn't used fgets and used gets instead, then we would be able to see what happens when we trip off this canary. Let me rename that actually to canary. And just to basically say what happens here is whenever the program starts, so we have our parameters here on the stack, we have our local variables, on the stack. This is basically going to set the canary to a random value. We're going to run through the program, and then before it returns, it's going to check and make sure, does this canary still equal the random value I set it to at the beginning? Because if it doesn't, I'm going to just exit the program and say stack smashing detected. So if we were overflowing the buffer, and we wanted to overwrite the local variables, or we wanted to overwrite the return address, then we would also need to overwrite this canary with its original value. So we need to maybe leak the value and then overwrite it with that value, otherwise we'll get that stack smashing detected. Again, I just wanted to touch on that very briefly, but we're not going to go into it in too much detail. Let's go and have a look at this Vuln. We have the same thing here, so we do actually have our canary as well, but there's no, let me go back there. What's it called? Global offset table overwrite.c. So there's actually no return statement in this Vuln function, if you notice. It's just supposed to keep looping through taking our input. Okay, we have our buffer here as well. So we mentioned previously that we can use the %n format specifier in order to write things, and we're going to look at that in detail in a minute. But what would we want to overwrite here? Well, we've also talked about the global offset table before, and if we go and have a look here, we've actually got a global offset table and a global offset table.procedure linkage table. And here we can see our Lib-C functions. Essentially the idea is going to be that we want to overwrite an address of one of these functions in the global offset table with a function that we want to call. So for example, the system function in Lib-C. So for example, let's see, we've got this printf here, right? If we were to enter in a value here to overwrite an element of the global offset table, we could find the address of printf in the global offset table and overwrite it with the address of system. And because this is a continuous loop, what's going to happen is it's going to loop around again. It's going to take an input from us, and then it's going to, instead of calling printf with the buffer, it's going to call system with the buffer. So if our buffer, if we just enter /bin/sh, this is going to call bin/sh. Not too complicated, hopefully. Let me just mention briefly as well. So we have our global offset table.plt, we've got our GOT here as well, we've got our PLT as well. And I just want to go and show, so there's a couple of articles here. I've linked one in the description to Ironstone, which, as I say, has got some great information on this stuff, the PLT and the GOT. There's also this other article which I'm actually going to take a look at, which I've left in the description, which I found particularly helpful at the time. And it just mentions that we basically have a global offset table, we have a procedure linkage table, and then we also have a GOT.PLT and a PLT.GOT. So you can go and have a look through the difference of these, but the TLDR, those starting with .plt contain stubs to jump to the target, and those starting with global.GOT are the tables of the target addresses. So actually, let me just go on that, let me just expand on that a little bit. So this is the actual table of offsets as filled by the linker, and the PLT is a stub which basically will go to the global offset table. So the stubs look up addresses in the GOT.PLT section and either jump to the right address or trigger the code to go and look up that address. So let's say, for example, the PLT, let's go back. So let's say we have these functions anyway. This is a stub which is going to call through to the global offset table, and if the global offset table doesn't already have the address populated, it's going to go out to the Lib-C library and find out where it is. I'll leave these links in the description, you can go through it in a bit more detail. It's not too important for us in this case, but I just wanted to mention it because I've been kind of talking about this as quite a simple idea of overwriting the global offset table, but there's a little bit more to it than that. Okay, so I think we've outlined that stuff pretty well. Let me just go as well and say, so I've left a couple of links in the description. One here was the article that we touched on last time, which has a good example of how the write operation works. I'm not going to go through that in this one because I've found another one, which I've also left in the description, which I found to be particularly helpful when going through this. So we're going to go through this example and compare it to what we're doing shortly. But just a quick recap then, if we run the program, let's run got overwrite. It's just taking input from us. So we can put in here, say we want pointers, and we're reading 3 pointers off of the stack. We can try to do %s. We get a segmentation fault because it's gone to this address. It's gone to try and print as a string whatever this address is pointing to, and obviously this isn't a valid memory address, so we've got a segmentation fault there. So just remember that the pointer and %x for hex, they will represent those values on the stack as hex in both cases for the x and the pointer, for the x and the p. But if we use %s, it's not actually just going to print what's on the stack as a string, it's going to go to that address and print whatever's there as a string. So I went through a fuzzing script in the last one, let's do that again. Let me just open this up, fuzz.py. Very basic script which just loops through 100 times and it's going to send off this x parameter to print whatever's on the stack as a hex value. And then if it's not empty, print it out. So you can see that this is all the addresses. Some of these are going to be things from Lib-C. Some of them are going to be functions in the program. Some of them will be strings that we've entered. So for example, this one quite clearly looks like we could unhex it. And we'll see this is actually what was entered there. It was the percentage for $x to print the 4th element off the stack as a hexadecimal value. Alright, so let's go and have a look at the details of the vulnerability. I'll try not to read this all out verbatim. I would recommend checking out this article, it is really useful. So we've got some of the different format specifiers that we can provide here depending how we want to represent the data. We can see a diagram of the stack here. So this is just like our example. Let me open that up again. Got overwrite.c. So in our example we have this printf of buffer. Now if we were to provide %s, what that would say is print whatever we've just entered as a string. Well, it would actually go to the address of that and print it, as we just mentioned, as a pointer instead. But that's just an example. But if we provided %s, it would then start printing all of the other things off the stack, which is exactly what you can see here. They've done %x 3 times and they're printing these various values off the stack. So we've got an example there. We've got an example of how to read a password from the stack. This is basically what we did in the previous challenge, although we used the %s because we had the... Oh, they're also doing the same here. It's a pointer. Okay, so yeah, exactly what we did in episode 7, I think it was. But this is what we're interested in, right into the stack. So we've got an example here, and in their case, the example, so they've got a target dead code, and the idea is to overwrite that with Cafe Babe. Now, ours is going to be pretty similar. Basically, we're going to have an address of our printf. So, for example, our printf is here, 804C00C. That's our target address that we want to overwrite. And then the address that we want to overwrite it with is system. We don't actually have system here, so we need to go and find out what that address is. But that's essentially, our goal is very similar. So we have an example here from the printf manual page which explains what the %n format specifier does. A better explanation of it is here. So it means that %n will write the size of our input at the address pointed to by %n. So for example, if we provided 4 A's %n, it means it will write the value 4 because A times 4, that's 4 characters, at the end, at the address pointed to by %n. But where does %n point to? So they're trying this as an example in the program, %n, get a segmentation fault, and that's because they've tried to write the value 4 to the address pointed to by n. Obviously that's not a valid address. So to solve the challenge, you need to remember 2 things. We can control the input, we can specify a position to read or write from the stack with %, the number, the index, and then $n. So instead of using %n, we can use %. That's what we've been doing anyway, so there's nothing new there. First, to write 0x Cafe Babe to the target, we need to find the target pointer on the stack. So you can see they've gone through there to basically find out where is Cafe Babe, where is it? It's down here. So it's the 23rd element off the stack, and they want to replace it. They want to replace that value. So if we can find the pointer AAAAA, we can replace AAAAA by a specific address to write. So you just recheck and see that it's the 7th argument. So we can do something similar here. Our write offset is not necessarily going to be the same. Let me go back and run that again. And let's try and enter that. Let's do AAAA %7 $P. And notice that we don't have A's in the response. We don't have 41, 41, 41, 41. So we could try and fuzz this. We could use a script like we saw previously, or we could just try and play around with it. Let's try and do $6 P. It's not that one either. I think we might actually be, alright, one more. There we go. So our offset is 4. So there's a 7, ours is 4. Just bear that in mind, it's going to be different from program to program, and you want to try and find out, basically, what you're looking to find out is the characters that you enter, what place do they get put to on the stack? Because that's the address that can then be used in the remainder of the write operation. So in their example here, they are writing, first of all, they're writing 4 to this address, because that's still 4 bytes. I'm going to go through the example. I'll not go through that here, but again, if you struggle with this, and format string vulnerabilities, I still struggle with them. They took me a long time to get to where I am, and I'm still not an expert in it, but go through this until you understand it if my video is not making it clear enough. So yeah, they don't want to write 4 anyway. We want to write Cafe Babe. So there's 2 issues. First of all, writing 4 characters means writing 4 at a specific address. So we would have to write this amount of characters in order to write Cafe Babe. Impossible. So here's a trick. So they specified here that in this case AAAAA %96x will write 100 bytes. So it'll write the 4 A's and then it'll pad the other 96 out with a space, which means you will see that in the terminal if you run through it. The second issue is you don't want to do AAAAA percentage and then the full number they had there, because it'll take a long time to write that out to the standard output. So instead of writing all 4 bytes at a time, we can write 2 short integers using this specifier hn. So if they want to write cafe babe, they can write cafe to the higher order bytes, the top 2 bytes of the address, and then 0xbabe to the lower order bytes. So we're doing 2 smaller decimal values rather than trying to write all of that at once. You want to write those at the values, so we're going to be overwriting AC plus 2, because the higher order, we're doing half of the address with cafe, and then the lower order with babe. We have to figure out a value for setting the padding, so here's the formula. The value we want minus the bytes we've already wrote equals the value to set. So let's start off here with the lower order bytes. So 47,806 minus 8, so that was our babe, minus 8 because we already wrote 8 bytes, which was the 2 4-byte addresses. And then the higher order bytes we'll do, because we've just written 47806 already, we subtract that from what we want to write. Remember, we want to write 51966, but we've already written 47806. So we subtract that and we get 4160. And they put this together as an exploit, so you can see here they have the exploit and then they break this down. So we have our first address in little endian order is the 2 lower order bytes, and then the higher order bytes in little endian as well, so we can see that here. And these are the 2 addresses that we're going to be writing to. And then remember, we have our 47798 bytes that we want to write here to we're doing the lower order first of all, and that's what's specified here. And then %7hn, this is %7 because their offset for the write was at 7. Remember, it was the 7th element on the stack. For us it was 4. And it's going to write 8 plus 47798, which were already written, equals 47806 at the first address specified. And then we have our 4160x, which is going to write 4160 bytes of standard output. Finally, we've got this %8$hn, which is going to write 8 plus 47798 plus 4160 equals 51966 in the second address. So they go through the example here. I know that sounds really confusing. What I've actually done is I've put together in Notepad let me open up manual exploit notes. I basically copied out what they have there and replaced it with what we need for our attack. So hopefully, if you're struggling with this, go through their example and then compare it to what I've done in this example here, where I've literally just replaced the values that we need with the values that we're trying to write. So let's try and go over this as well. So in our case, we want to overwrite this global offset table printf address, which we have here, with this Lib-C system address, which I've just found manually, but I've showed how to do that a few times. I'll not go through it again in this one. And we're going to use the same process. So rather than trying to write all that at once, we've got the decimal value here for the first half of the Lib-C system address, and we're going to write that to the higher order, so this address plus 2, and then the lower order, the other half, will just be at this address. So we're just doing 2 bytes at a time. And again, we've got the decimal value for that as well. So we have the same equation. We're going to start this off with the lower order bytes. We've got our lower order bytes here. This is what we want to write, and this is the decimal value. We've got minus 8 because we've already written 8 bytes. That's the 2 addresses that we specify at the beginning of our printf format string. And that's going to be then the value, so you can see the value here, that's what we're writing. And then we need to do the higher order bytes, but we need to bear in mind that the value that we want to write here is a 63455, but we've already written this amount of bytes already, 61504. So we need to subtract 61504. We then get 1951, and then we need to construct the exploit. Remember that our printf format string vulnerability, our write vulnerability, is at 4. That's the offset to what we enter, where it's going to be on the stack. So we're writing first of all to 4 and then to 5 for the next one, instead of 7 and 8 in their example. And then this is just put together. So we do the reverse endianness, we do little endian, so we reverse it. We put in our 2 addresses here, as we can see there. And then we're first of all going to write the 61,496 bytes, which is this value. Remember, we subtracted 8 because we've done our first 2 addresses already. So this whole thing is actually, let me copy all that. This whole thing is actually 61504 bytes. And that's what we want to write at the lower order. So that is then going to be written with our %4hn. We can see here it's going to write 8 plus the 61496 bytes, which equals our 61504, the value that we want here, the F040, to the first address specified, so our lower order bytes. We're then going to do the higher order bytes. We need, remember, we need the 1951 because we had to subtract what we've already written. And we'll do that then by specifying here %1951 hex. And then finally, we have at the end of this the %5hn, which is going to write 8 plus 61496 plus 1951 equals 63455, or F7DF at the second address. So we basically put all that together. Here was our payload. We just print that out in Python to a payload. And again, I've linked that down in the description, so you can go and take a look at this. I'm going to paste this in. Let's send that to manual payload. And we can have a look at that, manual payload. Oh. You can see, obviously, it's not printing out the addresses there at the start, but we have the rest of it showing. And then all we need to do is try to exploit it. Now remember, quite often what we would do here is run the binary and just send in the payload. But in this case, because it's going to be an interactive shell, we need to do it a little bit differently. We'll do here cat manual payload cat, and then we can pipe that to the global offset table overwrite. Let's try that. ls who am I? I'm root, so I can now cat out flag.txt. And there we go, we've overwritten the global offset table using our manual exploit. Look at all these spaces that we have in our terminal, and that's even whenever we manage to split that up into two segments. So hopefully that helped going through the manual payload. Let's go and see how we could also automate it with PwnTools. So there is actually this format string functionality in PwnTools where we can pretty much automate this and just call writes by providing in the function that, or the address that we want to overwrite and the address that we want to write it with. We have this execute writes functionality. So there's some documentation here. I just thought I'd bring that up in case you want to go and have a look through it, but I'm not going to read it out on screen. Let's have a look at our payload, exploit.py. Now one thing that's different here is that we have this send payload. Normally we had our function here to find the offsets to the instruction pointer when we're doing a buffer overflow. In this case, because we're using a format string vulnerability, as you can see here, we're using this function. You can highlight that and see it takes in a function which is called every time the automated process wants to communicate with the vulnerable process. Takes in the parameter with the payload that you want to send to the vulnerable process. Okay. So if the offset is not given, then try to find the right offset by leaking the data. Essentially what we do here, so we have the send payload function, and it's just going to call send payload, and this is going to go and try to identify where the offset is of the write operation. In our case, we know that the offset is 4, so we didn't actually need to use we could specify that to PwnTools, but we can also just let it do it automatically as well. You can see that I've specified the Lib-C library, and I've done this a little bit differently this time. Normally we would either provide the Lib-C as a binary here, remember where we did the elf and provided the location of the Lib-C library. In this case, we're actually setting elf.libc, so our vulnerable binary, we're setting the Lib-C inside of elf to equal Lib-C, and then we're updating the Lib-C.address to our address, which I've just got from LDD. So I've just pasted in this address. Again, if you followed the last video, we know how we can leak these stuff as well. So we actually have our printf format vulnerability in this as well, so we could just leak this. I'm just not going through all the same stuff that we did in the last video. I just want to focus on the write operation this time. So we print out anyway the printf in the global offset table, the address of it. That's the address we want to overwrite. And then we're also printing out the address that we want to write, which is the libc.symbols.system. Remember, this could also be a one gadget address as well, as long as you can meet the constraints. Remember, we looked at that in a previous video. But yeah, in this case, we're just setting it to system, and you can see I've got here a kind of manual format string write where we're saying let's do that lower order bytes, let's set it to lower half, and then let's do the same with the higher order as well. So like we did in our manual payload. So let's try that first of all. We're basically just going to execute the writes. It's going to overwrite those addresses, and then it's going to send the bin.sh, because remember, if we go back to our vulnerable function, if we're overwriting printf with system, it's going to call system with whatever parameter we've got as a buffer. So this wouldn't necessarily work overwriting all functions. You need to be careful what function you're overwriting, or you'll need to go and set some other things up in the program. Okay, let's save that. Let's go and try to run it. It runs through, we get a shell, we can cat out flag.txt, and you can go and have a look. PwnTools do this a little bit differently. In the past, whenever I've got stuck with format string vulnerabilities, when doing these write operations, I've often just gone and had a look to see how PwnTools do it, but it doesn't really do it in a way that's as easy for me to understand as doing it manually. So there is that. So you can see it found the format string write as well. It went through 4 times until it found that the offset was 4. Remember, in the example we looked at online, it was 7. So worth bearing in mind. Let's go and try and do it slightly more automated. So instead of specifying that, we're literally just going to say we want you to write over elf.got.printf with lib-c.symbols.system. We run that again. Again, we've got a shell. We're running as root, and the payload is probably exactly the same here. That's about it for this video. So we've seen how that we can overwrite elements of the global offset table using the printf format string vulnerability. In the next video, we'll look and see how we can bypass canaries. So in this case, we had canaries enabled, but we weren't actually doing a buffer overflow. In the next video, we won't have a printf format string vulnerability, but we will have these canaries enabled, and we want to see, can we leak the canaries off the stack and then overwrite them with the correct value to make sure our buffer overflow doesn't crash. And I hope you enjoyed this video. If you have any questions or comments, leave them down below. Thanks.